Okay, so chapter 9 starts talking about things called transformations. Okay, and you have done a little bit of this in algebra. Okay, whether you realized it or not is a different story. But let me show you what you do now. And this then becomes a very pervasive procedure throughout all of your remaining algebra courses, trigonometry, calculus, whatever you take. When I teach college algebra, I teach this about, we talk about it probably about 90% of the classes that we have in session. Okay, transformations are a topic that drives a lot of other topics in algebra. Okay, and they're simply this. You guys remember what this thing looks like? That's a parabola, right? Okay, and we could even do this going back to what we were talking about with circles the other day. Okay, if I take this parabola and I start adding things to it, so I'm going to take x squared and I want to add some number. I'm just going to call it a right now. It's going to let me put this a at the end of the equation. So it's either adding or subtracting. Okay, if I add, okay, it's going to take, I'm just going to add 1. And what we realize here, okay, is that this point, let's see here, this point here that was on the green curve just got moved up 1 unit onto the red curve. Does that make sense? This point right here, which was on the green curve, gets moved up 1 unit onto the red one. This point right there on the green curve gets moved up 1 unit to the red one. Does that make sense to everybody? So that 1 right there is showing how each one of the y values on this green curve becomes in a y value on the red curve. Is that okay with everybody? If that number becomes a 2, okay, it shows you that that distance right there is 2 now. So the y value on this curve, add 2 to it, you get the y value that's on the red one. Take this y value, add 2 to it, you get that y value. Take this y value, add 2 to it, you get that y value, right? Does that make sense? Okay. If I add 3, same idea. Okay, but now adding 3 instead. If I subtract 1, it's going to move them down. Okay, so you see the y value from A had a y value of 0, and now it goes to B, which is a y value of -1. So we just subtract going down. Is that okay with everybody? That's called a translation. Okay, and now because it's up and down movement, we call it a vertical translation. Okay, if I do this, and this is kind of where we saw it happening with circles the other day. Now I'm going to put like a minus or a plus with the x before I square it. So it's going to look something like that there. Okay. Now the point relationship's a little bit different, so I'll delete these. And what has happened now is that when I go -1, it actually moved it to the right. You guys remember doing minus h and minus k, and they moved counterintuitively? Okay, if it was minus, we thought it would move left, but it moved right. If it was plus, it moved, we thought it would move right, but it moved left. Same thing here. If it's a minus, it moves right. But how far does it move right? Well, this point here went 1 unit to the right. This point here went 1 unit to the right. That point there went 1 unit to the right. Does that make sense? Okay. And if I make that go to like a 3, that point went 3 units to the right. This point, 3 units to the right. And get back here. That point, 3 units to the right would be right there. Does that make sense to everybody? So that's a horizontal translation. Okay, just moving it, sliding it left and right. So if you guys remember, if I had x squared as my graph, and I wanted to find out what x minus 3 in that format. Look, so that graph right there and this green one, they're the same thing, right? Okay. And what we learn about, if we understand translations well enough, and you'll spend quite a bit of time in Algebra 2 and College Algebra doing this, is that I don't really like this, okay? Because this format only tells me my y-intercept. Tells me that 9 is my y-intercept. Because that's when x is 0, right? If x is 0, that goes away, you're left with only 9, okay? I don't really get anything else from this, okay? But from this format, I get a lot. I know the x-intercepts, I know the vertex, I know a lot of stuff from this red version, okay? Because I know a lot about this one. So basically what we do is we say, okay, I want to know stuff about this. So we convert it to something like this, and then our knowledge of transformations allows us to compare we call this a parent function, what we know about this, okay, which we know maybe 0, 0, 1, 1, 2, 4, those are points that are on that curve. We can quickly generate the points that are on the red one, okay? So what I'm trying to get at, and there's a lot there, that discussion's probably 2-3 weeks worth of actual discussion later on. Transformations allow you to take something that you are familiar with, okay, something that you're comfortable with, and learn something about a new object, okay, maybe a new function or whatever. All your graphs are this way, okay? So no matter what f of x is, so let's see if I can do something like this. Let's go input. It won't work. So what we can do is I could take, you guys know what a dilation is? When something enlarges, right? Okay, or shrinks. So let's say that I take, where did that thing go? Let's just start with our function being x. Let's do this. This is a graph that you'll realize in trig at some point, okay? If I take and multiply that by a number out in front, see what it does to that graph? Does it stretch it vertically? Does that kind of make sense? Okay, that's what we call a dilation in our algebra classes. We'll call it a dilation today in geometry, but it's ultimately what we call a vertical stretch in algebra, but just by multiplying by some factor. Okay, if we want to, so let's take a, and let's go here. Let's go plus a plus. I should go minus a plus b. So again, I'm going to start with the sine of x graph, which is the red one. So if I get everything back to zeros here, okay, that is what we call our parent function. Well, if I ever have something that comes across and looks like that blue one, which is different than the red one, okay? I should know that based on this, let's look at this. We know this moved it right. Does that make sense? So look at the red one. Would you guys agree that 0, 0 is on that red curve? Okay. So that point 0, 0 is on that red curve. This tells me that 0, 0 gets moved to the right 2.8 units. So I'm going to take 0 as the x-coordinate. I'm going to move it 2.8 to the right. So that means add 2.8 to it. Okay. This number says take your y value that is there, and you're going to move it 1.5 up. So start with 0 and move 1.5 up. Does it put that point then? It moved to the right and then up, and it puts it right there, correct? Okay. So let's do this. Let's see if I can take. Okay, so I'm just going to see if I can get that point to stay on the red curve. Get rid of B. So I'm going to do this. I'm going to say take the x value of point A, and let's add 2.8 to it, comma, the y value of A, and let's add 1.5 to it. Okay? And now as I move point A, point B moves along the blue curve the same way, right? Because every single time what transformations are showing us is that here, that distance right there and that distance right there are always 2.8 and 1.5 as we move A along here. Does that kind of make sense to everybody? Okay. And that's a transformation. So if I wanted to, let's say I didn't know what this looked like, but somebody says shift it right 2.8 units and then shift it up 1.5 units, I'm going to basically find this point right here. Okay. I'm going to move it to the right 2.8 and then up 0.5, and it's going to give me that point B. And then I'm going to do the same thing with this next point, and then the next point, and then the next point. And I'll move every one of those next points and the points behind it in the same exact manner. And if I do that with all the points moved the same way, I get that curve right there, which is this one. Does that make sense? So that is exactly what we're going to do today. All right, we're going to do it with geometric figures, but what I want you to realize is and you've done this in 8th grade, what we do here in geometry sets the foundation for what you're going to use in geometry. Let me rephrase, I said that backwards. What you do in geometry is going to set the foundation for what you do in Algebra 2, and what you do in college algebra, and what you do in trigonometry, okay? The better you understand it now, the easier transformations will be when you get into those courses, okay? And you can ask any one of my college algebra trig students how often we talk about transformations. They're going to tell you all the time, okay? So I show that because I think it's important. I've said this before. If you know where this stuff is going to pop up again and how frequently it's going to pop up again, maybe it puts more importance on it now, okay? Transformations, okay? We're going to have a series of transformations. We'll talk about, starting on that second bullet. We're going to have reflections, we'll have rotations, we'll have translations, okay? And those three types of transformations, okay, to transform something means to what? To change it, right? Okay, if I don't like my appearance, I don't like whatever, I can transform my appearance maybe, right? Does that make sense? I can change my appearance, okay? So when we see the word transformation, we're going to change something, okay? These three types of changes, reflections, rotations, and translations, are called rigid motions, okay? A rigid motion, the first bullet, is the action of taking an object and moving it to a different location without altering its shape or size, okay? A rigid motion is taking an object and moving it to a new location without changing its shape or size, okay? Another way of saying this, that when we do rigid motions, a feature that is important here is that distances are preserved. What does preserved mean? Say it again. Jams and jellies are called preserves, aren't they? Right? Why? They last longer. They don't change, right? Okay. I put up, I got jam, or I don't know if this is like healthy, but I got jam in my refrigerator that's like 3-4 years old. Tastes the same as it did. That's what's that. I don't feed it to my kids, but it tastes the same as today as it did the first day we bought it. Okay. They put preserves in like lunch meat and stuff like that, right? To keep it longer. Okay. Salt is a preserve. But it's to keep it from changing, right? Does that make sense? So when we say distances are preserved, that's the terminology that they use, but we could say distances are saved, distances do not change, distances are maintained, okay? And that is what we mean by not altering the shape or size, okay? The only transformation that changes size is going to be a dilation. So a dilation is not a rigid motion, okay? So that's that terminology. Now, a synonym for rigid motions is the word isometry. Okay. Sometimes we'll say that two things are isometric. Okay. When two things are said to be isometric, that is another way of saying that they are congruent. Does that make sense? Okay. So when we say that we have, basically, I don't want to say that congruency is the same as isometry, and isometry is the same as congruency. And isometry has the idea, the concept that we've moved a shape to a final position in the coordinate plane. And when that shape has moved to its final position, it is still congruent to the original shape in its original position. Does that make sense? Okay. And in order for that to happen, distances cannot change. Okay. So all of those reflections, rotations, translations, we should be able to take the final image and in some way move it, rotate it, reflect it to where it matches up exactly with the original image. Okay? Now, as we work through these, we're going to have sometimes multiple images in front of us. We want to be able to talk about those images easily, and so they're all on the same page. So instead of saying like original image or final image or something like that, we use this terminology. We say pre-image. Pre means before, right? Okay, so that's the image that we start with. Okay? We are going to do the transformation to that. Okay? So when you get into college algebra, those are what we call our parent functions, like x squared, x, square root of x, absolute value of x, 2 to the x. Those are all parent functions. Those are your pre-images. okay? Then something like x squared plus 6x plus 9, that's going to be the rule for your image, okay? Your image is the resulting or the end result after you've done your transformations, okay? The resulting picture or shape that the transformation has been applied to, okay? So pre-image is what you start with, image is what you get when you're done. Is that okay with everybody? Have you heard those terms before? Translation, often referred to as a slide. Okay, but slide is 6th grade to 8th grade terminology. Okay, so your end of course exam, probably not going to use the word slide. Okay, says you simply take the pre-image and you slide it, each ordered pair of the image in an X direction, followed then by a Y direction. Okay. Notation is one thing that can be problematic for people, and I want to show you the multiple ways you might see it because I don't know how the end of course exam will write it. Okay, they could very well on one question write it using what we call a mapping, and on the other question they can use subscript notation, but they really mean the same thing. So it says the notation can be shown using ordered pairs, and is referred to as a mapping. Okay, so a map, what's a map do for you? Gives you directions. Gets you from a starting point to an ending point, right? And that's exactly what this does. You start with an X comma Y. Okay? Doesn't matter what that X comma Y is, but that is on your pre-image. Okay? And this mapping tells you if you start with X comma Y, so let's say that the point -3 comma 5 was your particular X comma Y that was on your pre-image. What the mapping tells you here is that you're going to take the -3, which was your X value, and you're going to add 2 to it. And then you take your Y value and you subtract 4 from it. And ultimately, it gets you now -3 plus 2 would be -1. 5 minus 4 would be +1, right? This becomes then your image. Okay, so this is a generic mapping, and this would be like what you do with a specific value. Okay? But what that does, if you can do that addition and subtraction to every ordered pair that you have on your pre-image, what it does is it generates then your image. And because what we're going to do is predominantly work with polygons, the pre-image points that are nice to use are the vertices. Okay? If we go back to what I showed you at the beginning here, see here. If I start with something like x squared, excuse me, and we want to see, what does, let's go x plus 4 squared minus 5 look like. Okay. Would you guys agree? So we don't have corner points or vertices. This is called, we have one vertex. That's called a vertex right there. Would you guys agree that if I moved to the left 4 and then down 5, it gets me to that point right there? Okay. We have a key point called -1, 1 on the parent function here. If I move to the left 4, so 1, 2, 3, 4, and then down 5, 1, 2, 3, 4, 5, does it get me on that curve? Okay. So again, started with a point that I knew off the parent function, move it the same way that I moved A. So here's another point that we know, 1, 1. Move it left 4, down 5, gets me there. Okay. we should know another point 2, 4. So at some point, and I'm just going to start with 2, 4 here because it's off my graph right now. I don't know, because I can't go over and count now anymore, right? So let's say, so our rule would have said if you started with x comma y, okay, the mapping would have been you're going to move left 4 and then down 5, right? So let's say we know 2, 4 is on x squared, right? Okay, so if I start with 2, 4, let's subtract 4 from this. So 2 minus 4 would give me negative 2, right? And then 4 minus 5 will give me negative 1. So if I go negative 2, negative 1, is that a point on that graph? Does that make sense? I also know 3, 9. 3, 9 should be on this original pre-image. So if I try 3, 9, subtract 4 from the 3 gives me negative 1. Subtract 5 from the 9 gives me 4. So negative 1, comma 4 would be right there, and if we kind of extend it, we could see that that does go through that point, right? Does that kind of make sense what we're doing there? Taking points that you know are on that pre-image and either adding or subtracting to the x values and y values to get a point that is then on your image. That's what a mapping does, okay? And in college algebra 2, this is how those mappings are kind of provided for you, okay? This shows you that you're going to move left 4, and this shows you're going to move down 5 if you were to start with x squared, or the knowledge about x squared. So that's what we're going to try to do in geometry right now, okay? This is a structure that is, it's not used all that often, but I have seen it used on the end of course exam in previous years. So the T, the capital T, stands for translation. And that these ordered pairs, okay, is that 2 and that negative 4, tell you what is happening to the x's and y's. And because the 2 is positive, that means you're going to add to the x. And because the y is negative, that means you're going to subtract from the y. Now these brackets here, okay, they are not parentheses. They are angled brackets like that. And the notation for that, we haven't talked about this in this class. This class doesn't deal with this concept directly, but that's called vector notation, okay? And it basically, what it means is if you start with a point here, you're going to move 2 units that way. And a vector is what we call a directed line segment. So you move 2 units and then down 4 units, okay? And this should have been, I should have drawn it to the right if that's positive too, but every point, and that's what I was drawing over here earlier. I could grab a vector and basically says this is going to move to there, okay? And then it's going to be followed by that. Does that make sense to everybody? Okay, so we're always, and right now when we do translations, vectors are always going to be either horizontal or vertical segments, and they're perpendicular to one another, okay? But every single point then uses the exact same 2 vectors to get its position on the image. Is that something we can visualize or see? But that's why people always ask, well, why you call it an ordered pair, but why the corner brackets or the angle brackets instead of the parentheses? That's why, okay? All right, so I'm doing an example here. I want to take this shape and let's translate it. Okay, so let's go 3 and negative 4 like that. Okay, so if I were to write it that way, that is one process. Okay, that is one type of notation. Another type of notation is the mapping that would say if you start with an x comma y, okay, what does this 3 mean I'm doing to my x's in this notation? I'm going to write 3. And going right 3 is an additive concept, right? So x plus 3. And this minus 4 is going down 4, right? So it'd be y minus 4. So this notation means exactly the same thing this does. Is that okay with everybody? All right. Now what I would do is I would go find what these ordered pairs are. A, B, D, and C. So I'm going to write down A, B, D, and C. So I think this is a 10 by 10. It's actually 20 by 20, but it's 10 units that way, 10 units that way. So this point here would be negative 8, 1. Okay. B is going to be, so if that's 10, 9, 8, 7, 6, negative 6, comma 9. D is negative 1, 8. And then C is negative 2, 5, 1, 2, 3, 4, 5, negative 2, 5. Okay. Now the reason we choose the vertices and move only the vertices, because if we move the endpoints correctly for a segment and then connect them, then all the points on the interior of that segment should have been moved correctly as well. Does that make sense? Okay, so you're only going to choose those endpoints. You can do more if you want. If you want to move that point, have at it. If you want to move that point, have at it. Okay, it's just going to be more tedious for you. So I start with these. These are the pre-image. Okay, and they are going to go to our image. Now, what we generally do with our notation is we use the same letters for our image and our pre-image, but we put that little tick mark as a superscript, okay? And we read that as A prime, B prime, D prime, and C prime. Is that okay with everybody? I think we've used that notation in the past before. I think chapter 3 or 4, we used that a little bit, okay? But now all I'm going to do is say, well, A prime is going to be found by taking this pre-image, negative 8 and 1, and applying then this rule that says you add 3 to that, add 3 to the x value, subtract 4 from the y value. Does that make sense? And when we do that, we get negative 8 plus 3. I don't like how I did that. So negative 8 plus 3 would give me what? Negative 5. And then 1 minus 4 gives me negative 3. I'm going to do the same thing for B to get B prime. Add 3 to this, gives me negative 3. Subtract 4 from that, gives me 5. D prime, add 3 to that, will give you 2. Subtract 4 from that, will give you 4. And then here we got negative 2 plus 3 will give you 1. 5 minus 4 will give you 1. Now I'm going to go and I'm going to plot those points. So negative 5, 1, 2, 3, 4, 5, down 3. So that's A prime. Okay. B prime is at negative 3, 5. 1, 2, 3, 1, 2, 3, 4, 5. B prime. D prime is at 2, 4. And C prime is at 1, 1. And now if I connect those, is that new shape isometric to what we started with? Are they congruent? Make sense? And what is happening here, and some people like to do this, so a lot of times they'll ask you for those ordered pairs. Okay, so I think it's a good procedure or strategy to generate them that way. Okay, Some people are of the practice of not necessarily writing them down. I think if you don't write them down at some point, you might get yourself into a little bit of trouble later on. But if I take B and move it to the right, 1, 2, 3, and then down 1, 2, 3, 4. Take D, 1, 2, 3, and then down 1, 2, 3, 4. Same thing for A, 1, 2, 3, down 1, 2, 3, 4. Same thing for C, 1, 2, 3, and 1, 2, 3, 4. And we can get those points that way. Does that make sense? Okay. But we can shift left and right, up and down simply by adding or subtracting from the x values and from the y values. Is that something we could do? They like to reverse roles. Say, okay, we just did a transformation. Can you now tell me what this transformation is? Okay. So let's say that this is the pre-image, and this is the image. Okay, and they want you to write the rule. If there is only one translation happening here, this is pretty easy. Okay, or I guess one transformation. It looks directly like this one has been cut and pasted directly over here, right? And when you do cutting and pasting on your computer, that's exactly what you're doing. You're doing, or your computer in the background is doing a translation. So let's say I take this here and I cut it. Let's see here. And I move it. It's doing a translation. Does that make sense? Okay. Now when I move it to there, let me. Control Z, Control C, V. Okay. So they're identical. They're isometric. When I move it to there, okay, I'm now in the background, okay, because the entire screen here is a grid in the background of the program, and it knows that, hey, user just slid it X units or X pixels to the left and Y pixels down, okay. This would now be a dilation, right? So when you resize things on your computer, you're using dilations, okay? Some of your, and I don't know if I can do that here, can I rotate it? I can rotate it 90 degrees. I can flip it. I can do a reflection, okay? So these are all things that your computer does that we use on a regular basis that is programmed in the background of, in this case, Microsoft OneNote. It's programmed using the same structure or same geometry that we're doing right now. So if I want to figure out what was the translation, all you have to do is identify what you want it to be your pre-image. Okay, and usually it's the one without the prime. Okay, so that's my pre-image. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I move 9 to the right, correct? 9 right. And then I'm going to go 1, 2, 3, 4, 5, 6. So 6 down. Is that okay with everybody? So if I wanted to write a rule that takes an X comma Y, okay, from my pre-image to my image, that rule, 9 to the right, says you do what with the X? Add 9, right? What do I do with the Y if I'm going down 6? Subtract 6. Okay? That's the mapping. Or you could write it this way. Translation, 9 comma negative 6. Okay? A lot of textbooks like to use this here. That's a lot easier to write than what this is. Okay. Other ways you can do it, they could give you this ordered pair. They could say this ordered pair is negative 3, 9. And they can tell you that this ordered pair here is 6, 3. Well, if I look at the difference between -3 minus 6, that gives me -9, right? Okay. And if I go 9 minus 3, that gives me 6. So that tells me at least a quantity. Now, it doesn't tell me the direction because the order that I subtracted them. If I know that this one's getting moved to the right, then I know that that's got to be a positive. And if I know that this one's getting moved down, I know I need to make that one negative. But I could do it that way. Does that make sense? Okay. So that's how we do translations. Anybody have questions on translations? That pretty straightforward? All right. Reflections, okay, are a little bit more difficult, okay? So inside reflections, distance, again, is always preserved. It's an isometry. It's a rigid motion. So what that means to us is that they're going to provide us a line of reflection. They're going to provide us whether we want to reflect across the x-axis, the y-axis, the line y equals 3, x equals 10, whatever it may be. Okay, it could be any line. It doesn't have to be vertical or horizontal. It could be any line that we ever want to come up with. We can reflect over. Okay, but the distance from a point on the pre-image to that line is exactly the same distance as from that line to the corresponding point on the image. Okay. Now, here's my question to you. How do I measure or how do I determine distance from a point to a line? If I want to reflect this point across that line, what distance do I talk about, or what distance do we use? Because time we talk about this, that could be a distance to that line, right? Is that a distance to that line? Is that a distance to that line? But those are all different distances, right? What is the one distance that we always talk about when we go from a point to a line? What does this distance here look like it is in regards to that line? Is it perpendicular? And that means that's the shortest possible pathway from that point to that line, right? So that's what's going to happen when we do a reflection. Okay? This distance here has to, when I do a reflection, has to be the same as that distance there. Okay, if I'm reflecting that point. If I can do that with one point, I then do it with many points and connect them, and I've got my reflection. Okay, so down here is that being described in what we call this is called a horizontal reflection. Okay, and it's horizontal because let's just start with this as being the pre-image, and this being the image. Okay, it's horizontal because that's the direction that the pre-image moved. Does that make sense? It moved horizontally. Okay, but what we're seeing here is that all of these dotted lines are perpendicular to the line of reflection, meaning that distance there and that distance there are the same then. This distance here and that distance are the same. This blue distance and that blue distance are the same. Okay, so that's called a horizontal reflection. Okay, this is called a vertical reflection because now the shape, if this is the pre-image and this is the image, now we're seeing that the shape is moving vertically. Okay, now if I want to do a reflection, I'm going to say across the line y equals 0 here, okay, or the x-axis. There's a couple different ways notation-wise you're going to see this. They're going to use a capital R, and the subscript then, they will say, if it's one of your axes, a lot of times they'll say the x-axis, reflect across the x-axis, okay? Another way they can say this, what's the equation for the x-axis? Anybody remember? Algebra 1? What's an equation for the x-axis? Y equals 0. Y equals 0. Okay, so these two things say the same thing. All right. But if I'm going to reflect across the x-axis here, this point here at A, going perpendicular to the x-axis, that's 2 units, right? So then those 2 units need to be modeled right there. They need to be identical on the other side of the line of reflection. So A prime is going to go there. Is that okay with everybody? B, right there, that distance, okay, which is a distance of 8, needs to also be 8 here. So 1, 2, 3, 4, 5, 6, 7, 8. And that would be B prime. And now C goes 1, 2, 3, 4. So there's 1, 2, 3, 4 as well. And there would be C prime. And now if I connect those, this would be your pre-image, and this would be your image. Is that okay with everybody? What happens though, and then this is only going to work for a certain set of lines that are lines of reflection. This point here, A, was located at negative 6, 2. This point A prime is now negative 6, negative 2. B was at 1, 8 and is now at 1, negative 8. And C was at, 6, 4 and is now located at 6, negative 4. Look at these 2 points. What is the only thing that is different between those 2 points? The y value is negative, right? Is that consistent for those 2 points that relate to each other or correspond to each other? And is that consistent then for, I didn't write it, 6, 4 and 6, negative 4? Yeah. So what we find out, and I don't like using x's and y's, you can, but if I have the reflection across the x-axis of a point, and I'm just going to say at that point, I'm just going to use the letters A and B, okay, where because of their structure and their location inside those parentheses, A is an x value and B is a y value. Does that make sense? Okay. That if I do a reflection of A comma B over the x-axis, what that's going to generate is the point A comma, how did these, because all these A, so all these x values, negative 6, they're the same. 1, 1, they're the same. 6, 6, they're the same, right? But the y values were what to one another? Opposite, right? Well, if B is where I started with, what's the opposite of B? How do I write the opposite of B algebraically? Negative B, right? Does that make sense to everybody? Okay. So that is what we call an x-axis reflection. You're going to just change the y values by a negative. Okay. Let's go back to this here. And I'll just start with x squared plus 2. Let's start with that curve right there. Okay. If I reflect that across the x-axis, I get that curve right there. This was 0, 2, 0, negative 2, right? 1, 1, 1, 3 goes to 1, negative 3. Okay? Negative 1, 3 goes to negative 1, negative 3. Does that make sense? Okay? So the only thing there that changed was the y value got changed by negative. So if I'm going to write, so my original function is this, it was x squared plus 3. That was this top one. If I want this one here from that, the only thing that changes is the y value gets multiplied by a negative 1. So in order to go from that curve right there to this one, I'm going to write f of x equals negative, or sorry, I got to call it g just because of GeoGebra, negative what I started with, x squared plus 3, And when I do that, you see then it turned orange, but it gives this one. So if I have an algebraic function, and this is the connection that hopefully gets established with you when you get to Algebra 2. If you have an algebraic function, x squared plus 3, which is this one right here, and you want to reflect it across the x-axis for whatever reason, all you do is multiply the entire thing by a negative, because this is a rule that creates your y values, right? This rule generates your y values. And that's what we're seeing here in geometry, is that the rule says your x's stay the same, but you take whatever your y value was and you multiply it by a negative. And that will effectively give you an x-axis reflection. What do you think happens, or how do you think we should get a y-axis reflection? Okay, so a y-axis reflection, so reflection y-axis, or reflection x equals 0, okay, that's the equation for the y-axis. If I start with A, comma B, okay, so let's say I start with this point right here, which is at 4, 3. If I'm going to reflect it across the y-axis, okay, what's going to change? The y value is going to change. What's the y value going to change to? The x. So that distance right there needs to be replicated over here, right? So if I go from 0 to 0 to get to that point, I got to go left 4 and up 3. So this goes to -4, +3. So if I start with A, comma B, it's going to turn into -A, comma B. Okay? So this point here, and what's nice about that is then they say, okay, well, if I give you a point A, B, and C, and a lot of times they'll do this, they'll say, okay, well, B was located at 4, 3, A then is at 4, 5, 6, -3, and C is located at 10, 7. And that's my pre-image. And they want you to go to the image after reflecting across the y-axis. Well, if you know the pre-image is AB, then you take the opposite of the A, which would be -6, and you keep the B value alone, -3. Take the opposite of the A, so -4, leave that one alone, so 3. And then this one, -10, 7. Okay? And if you plot those points, it will give you that triangle over here that is the direct reflection of that one across the line y, or sorry, the y-axis, or x equals 0. That kind of make sense? Okay? So those rules are nice to use. Now, what happens, you guys are going to get a reference sheet for the end of course exam. The reference sheet is going off of memory right now. Let me open one of these up real quick. Reference sheet. This is the reference sheet that you get on the end of course exam. And as we go through, it's got your conversions if you ever need conversions. It's got your SOHCAHTOA and social right triangles, so that's a lifesaver for some of us. It's got this stuff. Okay. Area formulas, general volume formulas, got your distance formula, got your quadratic formula, got your probability addition rule, okay? But it does not have transformation rules, okay? I think it's important, I think it's useful because it's going to just quicken things for you. I don't think anybody's ever going to run out of time. You know, you get 3 hours, and I think it's in the ballpark between like 30 and 40 questions. Okay, there's 2 parts. One part's there's just the 2 parts that are a little bit structured a little bit differently. But usually one part's got 16 questions, the other one's got about 20. Okay, but you probably won't run out of time. You get 3 hours to do it. But if you're like pressed for time, like an ACT, it'd be nice to know those formulas for transformations so that you can do it efficiently and save some time on these problems. Because they can be tedious, time-consuming if you don't use the formulas. Okay? Or I don't know if I call it, they're just relations. I don't want to necessarily call it a formula. But that's how we reflect across lines. Okay? Now, those are only a couple of the lines. Tomorrow we'll start class with reflections across the line y equals x and the line y equals negative x. We'll reflect across like x equals 3, y equals 5, those types of things. Okay, so that'll start class tomorrow. Yes? Yes, I'll do that. I'll look into that here, 6th period. Collectively.